All right, thank you, Victoria. Next up, we have Luke Williams.
You guys are forgetting your phone numbers, you're in trouble. No, you should have known.
All right, hi everyone. My name is Luke. I was the group reporter for the jet engine experiment. Quick overview of what we're going to talk about today. So I'm going to go into the device we used, overview of the thermodynamic systems that are involved here, the data we collected, go into the analysis of the system. We're going to be looking at the enthalpy, the work calculations, the efficiency of the cycle, also the analysis of the compressor of the inlet of the turbine, followed by the power production, and then a quick conclusion. So this is the device we used. It's the Turbogen gas turbine electrical generation system, basically, which uses kerosene as its working fuel, and basically consists of a turbine engine and a generator to produce power based on the work out of the turbine. So this is the diagram of the system. You can see you have the two main group systems here. You have your gas turbine and your the electric generator, which is powered by this. This is a free turbine. It spins from the output of the turbine engine. So we did two data collection runs for this experiment. The first one, we're basically just looking at the turbine itself. So the control panel on the system, which Adam mentioned in his presentation, it has a throttle lever, and it also has it's a load lever for the generator, but basically it's a brake for the generator. And for the first one, that brake is locked in place, and you spool up the turbine, collect the data to look at the turbine itself, and then you shut that down. Then for the second data collection, you are adjusting the turbine brake, or the generator brake and the throttle for the turbine to look at power production, which I'll touch on later. And so the data we collected during this is the inlet and exit pressures and temperatures for the compressor. Same thing for both of the turbines. We looked at the turbine RPM for both, as well as the fuel flow rate, and the generator voltage and current, which was used for power out of the system. So this is data we collected. The numbers correspond to these points on the turbine diagram. So that we recorded pressures and temperatures for these locations, and then from that, using the air table or thermodynamic properties for air, you can determine the enthalpy at these points. So for the enthalpy, using the enthalpy to find the work for the compressor, H2 minus H1 was found to be about 122 kilojoules per kilogram. Energy added to the fuel, enthalpy difference again, 573-ish kilojoules per kilogram. The turbine work was about, again, enthalpy difference, negative 110. And then the work of the cycle, which is the work of the turbine plus the work of the compressor, which would be about 12.3 kilojoules per kilogram. So we used this to look at the efficiency of the turbine, which was found to be about 2.16% efficient, and also looking at the work done by the free turbine, which that's not part of the turbine itself, that's for the generator, but the work done for the free turbine was about negative 150.3. So then looking at the compressor inlet, which is just the very first part of this, is basically what's the air coming into our system. The density of air was found to be about 1.3. The velocity of the air entering was about 86 meters per second. The volumetric flow rate was 0.26, and the mass flow rate of air about 0.34 kilograms per second, and the Mach number was found to be about 0.25. So power produced, which is kind of the point of this experiment, is you're looking at power that's coming out from the generator powered by the turbine. So the peak power we got was about 10,000 watts, but the average power it was producing was about 333 watts, and this is because when you're operating this experiment for the second, this is looking at the second data collection run, you're continually moving the throttle and the brake levers, and you're trying to keep the RPM of the generator about as close to 8,000 RPM as you can get. That's kind of the ideal power generation speed for it. You can't go too high because you run the risk of the generator exploding, which would be very bad. So, and the system actually has a built-in safety procedure to where if that RPM goes above 8,000, when it gets to 10,000, it shuts off, which is what happened to us. We were trying to adjust, you have to adjust them inversely, so as the throttle goes up, the brake has to come down to try to get the power production ideal. And so I was adjusting it up and it hit that 10,000 RPM on the generator, which caused the system to shut down, which ended our data collection run. So in conclusion, our results were pretty consistent with what we were expecting to get. The efficiency was basically what we thought would happen. And the main takeaway from this is, why do we use these types of systems? So it's used for producing electricity, and when steam turbines, which is what's generally used for electricity production, during peak times those systems can't handle the demand that's needed. And so these gas turbine systems are used to kind of supplement, or they are used to supplement the electricity production for that given time. And then once the demand falls back below the threshold that the steam turbines can handle, they shut down and are not used again until they're needed. References and questions?
Question about your work of the turbine and the compressor? What it's like. So your work of the turbine is actually less than the work of the compressor, but the turbine is actually what powers the compressor. I don't understand how that is.
So the work of the compressor, which is what's coming under the compressor, right? So the work from the turbine, as you said, it powers the compressor. Honestly, I'm not really sure. Yeah, you're right. I guess it should be higher because it's powering that compressor. I don't know.
Did you plot the power versus thrust versus speed diagram?
So I didn't include them because there was they wanted 18 different plots, and I didn't think I'd have time to go through all of that. Basically, you plot use those plots to determine the point at which you would use data. So you plot the power to find.
So okay, that's fine. But your work on the cycle is negative now, right? Not positive. And your efficiency is negative or something.
Yeah, the work of the cycle was positive.
How? Because 110 for the turbine and compressor was 120, right? The work of the cycle should be negative 12.
I guess I'm in error.
It should be positive.
Yeah.
If he has negative 110,
If
that's
it's
his
Yeah, but the
turbine.
negative
compressor
110
plus
Again, what is
turbine.
turbine work should be positive, compressor work should be negative. Again, you took the negative sign to mean positive or exactly. Another means but this 12 for you, but positive 12 actually means negative 12, correct? The positive formula cardio sign convention means you're putting work into the system, correct? So it should be negative work.
Right.
Right. Which makes no sense. Okay.